Hi there. Welcome to part 22 of the Wireless LAN Security Mega Primer. So we started WPA a while back and now we'll continue that with WPA PSK in this video. So if you remember from one of the older slides, a quick recap, we had said that WPA was created as an interim solution while the 802.11 Standardization Committee as well as the Wi-Fi Alliance sat down together to create WPA2. Then we also spoke about the fact that WPA uses TKIP while WPA2 typically uses AES. Now, one of the other things also we discussed was both WPA and WPA2 actually have a personal and an enterprise edition. Now, the personal edition typically is WPA PSK, while the enterprise edition is the whole .1x and radius server for authentication and encryption. So now let's move on and understand a little bit more about what is happening in WPA. So if you remember, the biggest complaint about WEP was that basically you had these two static WEP keys available with the client as well as with the access point. And basically data used to be encrypted and decrypted with the same key. Now, what WPA actually does is it tells that first, there are no static keys, which is basically we will not use a static key for any kind of encryption, which is going to happen for data transfer. Instead, we are going to create dynamic keys on a per connection basis. So typically when the client and access point connect, let's say at time equal to 0, a set of keys are generated for encryption. Now the next time they again reconnect, a new set of keys are generated for encryption, right? What this means is that never would you end up using the same key pair to encrypt and decrypt data. So here's the big question. How are these dynamic keys then generated? So this is where WPA PSK or WPA pre-shared key comes in, which is one of the techniques. And this is also called WPA personal, as we talked about previously. So I think almost all of you may have configured your access point for WPA. If you haven't, it's a bad sign because maybe then you have WEP or it's open, which means someone could break in. So hopefully at least you've configured WPA, even if you've not fully understood what it does and how it works. Now, very simply, well, you would have gone ahead and entered a passphrase, which can be anywhere between 8 to 63 characters long. And now what happens is this passphrase needs to be converted into an actual usable 256-bit key, which is the WPA pre-shared key. Now, this is done by using a function called PBKDF. We'll come to what it is in a second. Basically, when you actually run the passphrase through this function, it has hashing algorithms and all of that, using which the output is a 256-bit pre-shared key, which is used on the client. At the very same time, you may go ahead and enter the same passphrase on the access point. This typically happens through the management interface, which could be a web-based interface. And the access point goes through the exact same process to generate a 256-bit pre-shared key. So coming to the function, what is it all about? Well, PBKDF2 is basically the password-based key derivation function, and it has been defined in full detail basically in RFC 2898. Now, I will not get into the exact details of how this hashing function actually works, but very simply put, it actually takes in 4 inputs. The first is the passphrase which the user enters. The second is the SSID of the access point itself. Then is the SSID length, which is of course the length of the SSID. And then 4096 and 256 for WPA PSK. Now 4096 actually stands for the fact that the passphrase would be hashed 4096 times by this function, and 256 is actually the size of the end key which is required from the function. Now actually the password based key derivation function can take in any arbitrary values here, and hence you could have even derived a 512-bit key if you liked. But in the WPA PSK case or WPA2 PSK case, this is practically stationary, which is 4096 number of times you would have to hash the passphrase within the function, and the end output would be a 256-bit PSK key, or the pre-shared key as we call it. So now what we've learned till now is basically how to derive the pre-shared key using the passphrase, right? Now here comes the second part. How is the dynamic key derived? And this is what we are coming to. And in WPA, this happens, WPA PSK specifically, this happens using the four-way handshake. So how does it work? Well, the client and access point both need to be configured for PSK. And then first, of course, you have the probe request, probe response, auth request, auth response, typically using open authentication. And then finally, the association request and response happens. As we saw in the previous video, typically in the beacon frame as well as the probe request response, the whole security policy of what needs to be used, whether it is WPA or WPA2, PSK or whatever, is actually negotiated. Now, at this point, what do we have? Well, basically, we've finished the association and we are about to derive the key. So some quick nomenclature here. As we move ahead, we'll call the client the supplicant and the access point the authenticator, right? This is actually 802.1x parlance, which we'll come to a bit later. Currently, just remember, supplicant stands for the client or someone who supplies the credentials, if you think about it. And authenticator, of course, is the one who's trying to authenticate the supplicant, right? So till now, what we know is both of these have derived the same 256-bit shared key from the passphrase entered by the user, right? Now, here is what happens. The authenticator or the access point first generates a long random value called a nonce, right? This is just a long arbitrarily random value which is created, and it sends it as part of message 1 of the four-way handshake to the client. Now, this message contains a lot of fields. Let's quickly look at the field which is of importance to us right now. Now, this is taken from the IEEE doc itself, so due acknowledgement there. So basically, we have the key nonce, which is basically currently a nonce or authenticator nonce, right? And one of the important things to remember is the key replay counter is actually set to n, which is some value based on previous history, etc. Let's not worry about it. It's set to some value n, right? There are other things as well. For example, key information has the descriptor version, which could be either your RC4 HMAC or your AES along with HMAC SHA-1 and all of that. Let's not worry about it for the time being, right? What we need to remember is a random long value called the a nonce or the authenticator nonce is part of the first message which was sent as the first message of the four-way handshake. Now, the client, as soon as it receives this packet, goes ahead and creates its own S nonce, which is the supplicant nonce, which is another large random value, right? Now, here is what happens. We said dynamic keys need to be derived, and now the client goes ahead and derives a dynamic key. And this is called the PTK or the pairwise transient key. Now, one of the other names given to the pre-shared 256-bit key is the PMK or the pairwise master key. Well, as you can imagine, the reason why it's called master is it is actually being used in the process to actually create the transient key every time the connection happens. So if you note, we are talking about one exchange, one four-way handshake. The next time these two connect, the pre-shared key still remains the same, which is also called which is actually the PMK in this case. We'll see for WPA2, PMK would be something else. The way it would be derived would be somewhere different. So for the time being in WPA PSK, as well as in WPA2 PSK, the PMK or the master key is actually the pre-shared key itself. Now, what the client does is when it receives the authenticator nouns, it creates its own supplicant nouns, which we know are two large random values, and then it generates its own PTK or the transient key for this session, right? So before we go ahead, let's actually take packet by packet and break everything up in Wireshark, right? Before we actually get confused with what is happening. Actually, why don't I just take one step back and start with message 1. So what I've done is I have an access point which has been set to WPA personal to use TKIP, and there's a pre-shared key which is already given. Now let me go to our backtrack machine, and what I will do is let me start arrow dump. Right, and let me actually save everything up in a file called WPA PSK demo, right? So this is our access point configured for WPA PSK. If you notice, it is SSID is D-Link. Now let's launch Wireshark. And let's start sniffing on Mon0. Looks like there was some little problem. Hold on. I have a small memory issue here. This was from a previous capture. So let's launch Wireshark. And let's start sniffing on Mon0. So now the sniffing has begun. Now actually what we are interested in is D-Link. So let's go ahead here, apply a filter for this specific BSS ID. We hate peak and frames, so we'll just remove them. Let's start the sniffing once again. And now, as always, I will use my handy iPhone to go ahead and connect to this access point D-Link, right? Hopefully it's going to auto connect in just a bit, and yes, right, I've already fed the key to it. That's the reason why it kind of happened so fast. So let's go up. And one of the things you would kind of notice is, even though it's a four-way handshake, here is what I've seen unusually in my experience. Many a times Wireshark is not able to capture all of the packets. Just don't know why. So we could just hit ePOL and you would notice we have 3 packets but not 4. Let's go to arrow dump and you would notice it actually says WPA handshake has been captured, right? So arrow dump gives an indication if it was able to capture the four-way handshake which we are talking about right now. And in my experience at least, I've seen that arrow dump does a much better job at capturing these packets compared to Wireshark. I really don't know why, I can't explain it, but if you run the experiment 10 times, you'll notice Wireshark may miss a couple of ePOL packets here and there. So let me go ahead and run Wireshark with what we've just created, right? And inside this, all I really care about is the ePOL packet. And if you notice, even right now we've only got 3 of them. The funny thing is we could still crack the PSK with just 3 keys, but because we are learning, I think we should just go ahead with the capture once again. So the reason I'm going through this frustrating experience is it's happened to me more than once, right? So where I was not able to capture all the 4 packets, right? So let's start this off once again. And the client is connecting. We should momentarily see all the EPOL packets. Unfortunately, we are not getting all 4 of them. Let's reconnect. And this is something you won't believe I wasted a lot of time on, even though we are on the same channel. For some reason, the EPOL packets are pretty elusive, right? So I guess back to square one. One of the other techniques, of course, is to send the deauthentication. Okay, here we are. So we have all the 4 packets with us, hopefully. Let me just quickly verify this in a second. I have a little trick way of verifying that we actually have all the 4 packets. I'll teach you that a little later. For the time being, at least let me ensure that we have all the packets. Yeah, so we have all the packets. This is actually just a replay of the same packet, if you kind of notice. So don't go by this message 1 or 4, etc. I've seen Wireshark is typically confusing and not writing a message 3 or 4 in the right place. Anyway, so let's get back. So we've gotten all of this. This is a retransmission of the same packet. So we'll start from this packet, which is the second one here. Awesome. So let me bring this up a little bit so that we can see the entire packet in its beauty. And let's go back to the presentation once again, and let's look at message 1. So we said in message 1, the key replay counter is going to be set to 1 value, and then key nonce is set to the authenticator nonce, right? Let's go here. This is message 1, and what we would actually notice is that here is the replay counter, which has been set to the value 28, and here is the AP nonce. And if you notice, this packet is going from the access point to the client, right? From the access point to the client, right? The client is my Apple iPhone. Now let's go back to the presentation once again. And we said that once the client receives the packet, it's going to create its own S nonce. And from that, it's going to derive the PTK, or the pairwise transient key. Now, how is the pairwise transient key created? We'll get into the specifics of this in a later video, but to keep it simple here, the PTK is some function of the PMK. Actually, there's a little typo here. This is actually the PMK, the authenticator nonce, the supplicant nonce. If you notice, the authenticator nonce was sent by the access point, supplicant nonce by the supplicant, the authenticator MAC address, and the supplicant MAC address. And if you notice, at this point, the client knows the authenticator nonce because it was received as part of message 1. The supplicant nonce is created by the client himself, hence it knows that as well. The client also knows the PMK, which is nothing but the pre-shared key, and it is also aware of its own MAC address and the authenticator's MAC address. And using all of this, it actually creates the PTK, or the pairwise transient key, right? Now, what the client does is it sends the message 2 of the 4-way handshake, and this message 2 actually contains the supplicant nonce which it has locally created to derive the PTK. We can look at this if we go back here, and this would be that message which now the client, if you notice, is sending to the access point, right? Let me just go to the next slide to kind of draw a parallel. Okay. There are two things in this message too. One is of course the supplicant nouns. The other thing to note here is the key replay counter is still set to n, which was the same as message 1, right? So if you notice in message 1, the replay counter was 28, and right now in message 2, it still remains as 28, right? This is an indication of how you can pair the A nouns and the S nouns messages sent from first the AP to the client and client to the AP. Now, a couple of other important things here. You also have something called the key MIC, which is created. Now, MIC is actually a message integrity check, and basically there's an algorithm for it called the Michael algorithm. We'll come into all of that much later. The MIC, if you notice here, is created over the entire EPOL keyframe with the MIC field itself initialized to a 0. Now, people who remember from the IP TCP world, this is very similar to how you would calculate things like TCP checksums and all of that, right? Keep that field 0, go ahead, do all your mathematics, and then put the checksum field back there. So these are the three most important things, and if we come here, you would notice that you would actually be able to see the MIC and the replay counter and the S nouns sent by the client, right? And you also have something here where the client sends a lot of information, and the protocol actually defines that as well. It says the key data includes the RSN information element, which basically here is the STA's RSN information element, right? This talks more about the various capabilities of the client itself. Now let's go back to the presentation. So at this point, something very interesting happens. See, even the access point now knows, of course, the pre-shared key. It of course knows the A nouns because it was the one who created it. And now it also knows the S nouns, which was sent by the client. It knows its own MAC address. It also knows the client's MAC address. And hence, it can also derive the same PTK as the client. Now, what it does is the MIC is actually created using the PTK over the entire frame body. So the access point now also goes ahead and calculates the MIC. If the MIC matches the one which the client has sent, that actually means the client has also ended up deriving the same PTK, which would mean the client also knows the exact same PSK, which is the pre-shared key. And hence the access point is all happy about it. And the next message it would send is the key installation message. However, at this stage, if the MIC calculation does not match with what the client had sent, the access point would send back a deauthentication message saying that, well, you could not really validate that you knew the pre-shared key. Anyway, so message 3 is more of a key installation message, and typically important things here is in the key information field you would have install, which would be set to 1, and in the replay counter you would have n plus 1, which would mean we should have 28 plus 1, which is 29. Let's verify that in the packet. So we'll go to the next packet now, which is sent by the access point to the client, and if you notice, the replay counter now is 29 as we rightly guessed. Also, the install flag has been set, which means the access point is telling the client to go ahead and use the key as the PTK or the pairwise transient key for the current session. Of course, there's also an MIC with which validation can happen again by the client itself. So now, moving on, the client, after it goes ahead and successfully installs and uses the key, will send the final message, which is pretty much something like a key install acknowledgement telling the access point that, hey, I've gone ahead and installed the key. You can also go ahead and use the same pairwise transient key for the session to encrypt everything, right? And this is how this would look like. The key ACK would be set to 0, which indicates that this is the last message of the four-way handshake. And the key replay counter would again be 29, so that it knows that this is the matching fourth message for the third one. And this is exactly what it is here, right? The replay counter is 29, and basically the acknowledge flag is set to 0, which actually means this is the last message. Right? So this is how you can break up a four-way handshake. Now the first packet and second packet are pretty much the same, it's just a retransmission. So you can also see the R bit has been set. And this is where basically by looking at all of these packets, it is possible to go ahead and figure out what is really happening in an ePOL exchange where the four-way handshake happens and the pairwise transient key is derived using the pairwise master key, which is nothing but the pre-shared key, which was derived from the passphrase the user entered, right? So let's do a very quick recapitulation of what we've learned till now, because I can assure you this is not a very easy topic. So very quickly, we wanted to generate dynamic keys. The user entered a passphrase. We sent that through a hashing function that created the pre-shared key. The same key was derived by the access point. And from there on, basically, both of them have the same PSK, 256-bit. First message was sent with a random value called the authenticator nouns. With the authenticator nouns, the client also went ahead and created something called the supplicant nouns, which is another random value. Using the A nouns, S nouns, the pre-shared key, and the MAC address of the client and the access point, the client derives something called the PTK, or the pairwise transient key, which is what will be used for encryption in this connection. Then it goes ahead and sends back the message to with the S nouns in it, along with the MIC, actually, which I kind of forgot in the previous image. The access point generates the same PTK using the same variables, verifies the MIC. If it is correct, goes ahead and sends the key installation message. The client installs the key, sends an acknowledgement back to the access point, which also ends up installing the key. And basically, everything is all good. We are all friends, and data transfer starts between the client and the access point, right? So acknowledgements is the IEEE standard. All those little clippings of the message was taken from the standard as is. You could read that if you want, but it's quite complicated. Okay, so what happens if we don't know the right phrase? Well, as one can probably do a quick thought experiment, when the client actually sends message 2 of the four-way handshake consisting of the S nouns and the MIC, the authenticator or the access point also derives the PTK based on all of these inputs. And because the passphrase was entered wrong, the PTK as derived by the access point and the PTK as derived by the client are different, and hence the MIC does not match as compared to what the client had sent, and hence the access point figures out that the client does not have the same pre-shared key, and it sends a deauthentication message, right? So let's quickly look at this part of the whole deauthentication message. So let's restart the whole sniffing. This is a long video, guys. I don't even know how many of you are still watching or awake. So if you are, just write a comment saying, hey, I was there till the end. But I can tell you this is a damn complicated topic, and that's the reason I want to really go ahead and finish it off at one shot. Just a second, I'm just clicking on forget the network so that we can restart the whole process, right? And let me try connecting now. Now I'm going to enter a wrong passphrase, right? And typically this should fail for what it's worth. It says here, I don't know how many packets we've gotten. So let me just quickly go ahead and clear this expression to figure out what's happened here. And I guess we're not able to get all the packets. Let me just remove the beacon frame so that we can see a little bit of. And then what we also want is only our D-Link. Right? And we can see the deauthentication messages being sent by the access point to the client. Right? Actually, we are missing one of the messages, and I think if we go ahead and just kind of redo this entire thing, we should be able to get it. Let me try this quickly. Right, we are still missing the second message. Let me just quickly try this once again. One of the most challenging things with Wi-Fi is actually sniffing, because everything is happening so fast. It's almost so difficult to get all the packets which are up in the air. Let me just enter something random. Awesome, right? So now we have both the exchanges, and as expected, first the access point sends the first packet to the client, right? And this is going to contains the A nouns and all of that, if you remember, right? And then the client responds back to the access point, this time with its own S nouns. Of course, what it does is it also calculates the MIC over the entire frame. Unfortunately, because the passphrase is wrong, this MIC is incorrect, and hence the access point goes ahead and sends the deauthentication message to break the connection, right? Awesome. Hola, let's go back. Okay, this brings us to the end of a discussion of WPA PSK. Hope you've understood the four-way handshake, how from the passphrase we end up with the pre-shared key, how using the pre-shared key and the four-way handshake we create the PTK or the pairwise transient key, which is used for encryption for the current session, right? Well, that's all for this video. Pretty long one. Hopefully many of you are still here. Please leave your comments behind. I'm eagerly waiting for them. And in the next video, we will look at how to use this entire four-way handshake to crack WPA PSK. That's all for this video. Thank you. Bye-bye.